we now talk about some of the techniques for so called physical synthesis. Like when we say physical synthesis, what we actually mean is we are trying to adjust or control some of the negative slacks. So, when you do timing analysis, static timing analysis on a netlist, we may find that some of the nets they are having negative slacks. So, some corrective actions need to be taken. So, the required arrival time is less than the actual arrival time. Okay. So, for those cases you need to carry out some kind of corrective steps. This is what is meant by the so called physical synthesis steps. So, we start our discussion on this. So, physical synthesis, as I said, is nothing but a collection of timing optimization techniques. The main objective for doing this is to try and control the negative slacks, try and eliminate the negative slacks, make them 0 or positive. So, earlier we had seen what a timing budget is. So, this can consist of creating some timing budgets, and based on these budgets you try to check whether anywhere this budget is getting, you can say, not satisfied. So, you try to satisfy these budgets at every point in the circuit, and whenever you see that there is some kind of a violation, you try to take some corrective steps. Now, here we shall be looking at what are the possible corrective steps we can take in order to control these kind of timing violations. So, when we say timing budgets here, they include target delays along means either an entire path or along shorter segments of paths which are the nets. This can be done either during placement or routing stages, or also can be done later on during timing corrections. That means, you see after doing everything that some of the timings are not getting satisfied. So, you can carry out these corrective actions then also. Broadly speaking, timing corrections can be done using 3 approaches. First one is referred to as gate sizing, second one called buffering, which involves introducing buffers in the netlist, and third one is by modifying your netlist in some way. This is called netlist restructuring. Okay. So, let us start with the first one, gate sizing. This is a very simple and a very commonly used technique for adjusting the delays in a circuit. Now, one thing you observe is that today, as I said earlier, most of the VLSI circuits that are manufactured, they are based on the semi-custom or the standard cell design style. So, what is the basic idea there? We have a technology library where there is a set of cells which are pre-designed and are kept in the library. They are all of the same height, their widths can vary. So, whatever is required, I pick up a cell from the library, I put it in my layout, and the layout is nicely arranged in terms of rows. Now, what we talk about here is that, let us take an example. Let us say I need a 2 input NAND gate. So, I expect that in the library there would be a 2 input NAND cell. There is a cell indeed, but not just one. There can be multiple such 2 input NAND gates where the sizes of the gates vary. So, I shall explain what this varying of the size means. Okay. So, what I have just now mentioned is that each logic gate or the simple functional blocks which are supposed to be there in a standard cell library are available in multiple sizes. See, roughly speaking, a larger gate will have larger current driving capability. That is why we say here is that they can have different drive strengths. Larger gate will have larger current driving capacity, smaller gates will be having less current driving capacity. So, this drive strength actually determines the current which the gate can provide to the load during switching. Now, this is an important point, I shall be explaining this. So, when a gate is driving some other gate, the gate output actually faces load capacitances. So, on what factor does this capacitance depend? It depends on the fan out, how many gates it is driving, and also the size of the driven gates. Okay. Let us try to just explain this fact. Let us look at a simple example, 2 input NAND. So, I am showing you a CMOS level transistor level realization of a 2 input NAND. So, in the pull down you have the 2 N type transistors NMOS, and here you have the PMOS transistors A and B, and this is the output, let us say F. So, here this is A, this is B, and this is F. Now, the question that we are trying to ask is that, well, how small can our transistors be? Now, if you look at a transistor, say from a top view, a MOS transistor, there is a region which is the channel. This is the channel. On one side you have the source, on the other side you have the drain. So, current will be flowing in this channel. Now, the question arises, this is source, this is drain or the reverse, and this is the channel. Now, the question arises that what is the size of this channel we need to use. Now, you see, from natural optimization point of view, why should we unnecessarily make a gate larger, the channel larger? We try to use it as small as it serves my purpose. You see, the sizes of these channels, they are all based on some kind of feature size. This is a very standard technology or standard procedure. A channel can be minimum size 2 lambda by 2 lambda. This is the minimum feature size, it is called. And there is another thing, that the PMOS transistors, their mobility, that means hole mobility, is slightly less, that means the holes move slightly slower as compared to the corresponding electrons in the NMOS transistors. So, to make the switching speeds comparable, the PMOS transistors are made slightly bigger. You see, you can make a transistor like this, you can make a transistor like this, 2 lambda by 4 lambda. I mean, you can make it like this, 2 lambda, 4 lambda, or you can make it a square larger type, 4 lambda by 4 lambda. There are so many ways you can change the size of a transistor, means the channel. So, when I say the size of a transistor, means I refer to the size of a channel. Now, what I am saying is that, well, assuming that this p type and n type are all identical, but actually p type will be slightly bigger because of the mobility issues. So, the basic transistor size is 2 lambda by 2 lambda, we refer to as 1:1, 1:1, 1:1, 1:1. So, this 1:1 refers to the case that the length and the width are the same. But suppose I make the channel wider. So, I make the channel wider like this, that means source is on one side, drain is on other side. So, because it is wider, the resistance will become less. So, if the resistance has become less, it can drive more current. So, what I am saying is that I can make a gate larger, so called larger, by changing the dimension to, say, instead of 1:1, I can make it 1:2, something like this. So, I make the gates wider. So, if I make it wider, it can drive more current. So, the basic idea is something like this. And just another thing you just see, that suppose this gate is driving similar to other gates. Similar gates means what? The output, let us say this is F, this F is going to the input of another NAND gate, let us say. So, this point will be connected to one p type transistor and it will also be connected to one n type transistor, like this. So, for every transistor the gate to substrate capacitance is quite substantial. So, as an equivalent circuit we may recognize or we may treat that it is driving a capacitive load CL. So, this capacitive load is dependent on the fan out. If there are two such gates, the value of CL will be double, because there is another such pairs of transistors that are being driven. Okay. So, this fan out determines the load capacitance, and when we say that the output of a gate is changing from 0 to 1 or 1 to 0. So, when I say it is changing from 0 to 1, which means the capacitor was initially discharged, output was 0, now it is charging, this is VDD, it is charging via this path. Now, when I say that the output is going from 1 to 0, we say that it is discharging via this path. Okay. So, this charging and discharging time will depend on two things. One is the value of the capacitance, larger the value slower will be this process, and the resistance along these paths. Lower the resistance, faster will be the charging discharging. So, if I make a gate larger, this charging discharging will be faster. So, my gate delay will be less, right. So, this is roughly what we mean by sizing of a gate, how we making a gate larger can reduce its delay. So, we are not going into the further detail inside this MOS level designs, but I think this much is sufficient to know and appreciate that as I make a gate larger, which means I make my transistors wider, the channels wider. So, I can drive more currents. So, my RC delay will become less. So, the gate delay 0 to 1, 1 to 0, rising and fall time delays will become less, and more the number of fan outs, higher will be the capacitive load, more will be my delay, because I have to charge larger capacitance. Okay. Fine. So, let us take an example. Suppose we have a gate V and there are three versions of the gates which are stored in the library. Size of A is the smallest, size of V A is less than size V B, less than size V C. So, this is something which you have already said. So, if a gate has larger size, which means it will have lower output resistance and which can drive a larger load capacitance with possibly the same or less delay. Okay. Now, there are two things. So, if you make a gate larger, there is another point which is also coming into the picture. So, if you are making a gate larger, you are making the channel larger in size. So, inside the gate there will also be an intrinsic capacitance which will be coming into play here. So, earlier we were talking about the load capacitance when some other gate is driving another gate, but now I am thinking of the same gate. Inside the gate there can be some intrinsic capacitance between the channel and the grounds, various other things, layers. So, when the load capacitance is large, so this intrinsic capacitance will not matter much. So, as you make the gates larger, your delays will become less. So, this relationship will hold. This is for the case when the intrinsic capacitances are small and the load capacitance is larger. So, charging discharging time will be the predominant delay here, charging the load capacitance and discharging the load capacitance. Okay. So, since V A is the smallest, this the delay of V A will be the largest, V C is the largest, delay will be the smallest. Okay. But if the reverse is true, So means assuming that we do not have an appreciable load capacity, it is small. So now the intrinsic delay will dominate, and so if you make a gate larger, its delay will also go up. So by making a gate larger, whether or not the delay will go up or go down, it depends on number of things. You must also look into that, whether it is driving a high capacitive load or it is not driving that higher load. Depending on that, the delay might either go up or may go down, right. Okay. Fine. And another point is that if you increase the size of the gate, it may also affect the delay of the preceding stage, because you see, let us come back to this diagram again. Suppose if I make these gates larger, and if there is some other gate from the previous stage which is driving this, so this will also be facing a capacitance. So if I make this gate larger, the value of the capacitance is proportional to the area. So if I make the area larger, this capacitance value will also become larger. So this delay will also increase. Okay. So this is something you also have to keep in mind. All right. Now this chart actually shows you some representative values for the three cases, like this A, B, C, where I said that A is smallest and C is the largest. Size of A is less than size of B, less than size of C. So this graph shows the variation of gate delay with load capacitance. So load capacitances are plotted in femtofarads and delay in picoseconds. So what this graph actually means, so means I am showing one. Suppose if the load capacitance is 2.5 femtofarads, then with your smallest gate A, your delay will be 35 picoseconds, with B it will be 30, with C it will be 27, right. So for the various load capacitances, these are the typical variations that have been seen. So here we shall be taking some examples which will be using these values for illustrations. That is why I am showing this graph. Fine. So resizing transformation, what it says? It says that I change the size of a gate to achieve a lower delay. Like suppose I have a circuit netlist like this. I take one gate, a 2 input NAND gate which is driving 3 other points. Let us assume that the sizes of these destination gates are different and their total load capacitances are like this: 1.5 femtofarads all, 1.0 and 0.5. Now because this capacitance will lie in parallel, as you know, if the capacitances are in parallel, the total load capacitance will get added up. So the total becomes 3 femtofarad. So I am showing two alternatives. If I use VA, that means smallest gate with a load of 3 femtofarad, let us go back, with a load of 3 femtofarad, VA, the delay is 40. So for this case, the delay of the gate will be 40 picoseconds. But if I use a larger gate, VC, so you see VC, the delay is 28. So this gate will be 28. So you see, just by changing the size of the gate, I can change the delay from 40 to 28. So it is quite a wide variation that I can make by adjusting the size of the gate. Okay. All right. This is what I have already said. Fine. So the next technique is called buffering. Buffering means we introduce buffers in a circuit in order to achieve something. That something, let us see what are the characteristics that get improved by introducing or inserting buffers in a circuit. So what is a buffer? Buffer is typically constructed using a pair of inverters, or if you want an inverting buffer, then a single inverter can also suffice. Okay. Buffers can help you in doing a few things. First, speeding up the circuit or by serving as delay elements. Okay, this is a point we shall be again talking about later. The idea is as follows. Suppose I have a source, I have a destination, there is a wire connecting that. So, if the length of the wire is L, so the delay of this wire, if you just compute the Elmore delay model and compute the distributed RC model, so the delay of this interconnection will be roughly proportional to the square of L. So, now let us say I make a modification. Instead of this, I insert a buffer in between. I break this total length into two parts, L by 2 and L by 2. So, let us say the delay is equal to some constant k into L square. So, in this case, for the first segment, the delay will be k into L by 2 whole square. For the second part, again the delay will be k into L by 2 whole square. So, if you add this up, what will be the total delay? L square by 4 and L square by 4, it will be k L square by 2. So, the delay has become half. So, by introducing a buffer, we can reduce the interconnection delay. Okay. This is a very interesting and important technique for reducing delay. So, this is the first thing, speeding up the circuit. Second is modifying transition times to improve signal integrity. So, what this says is that suppose I have introduced a buffer in a circuit and my input signal, it is not very good, it has become like this. So, instead of a neat pulse. So, when I have a buffer, in the output of a buffer, I will again regenerate the signal into a nice pulse. This is what I mean to say, is that signal regeneration. So, as signals propagate over a distance because of RC effects, so the contour of the signal gets degraded, okay? The nature of the signal gets deformed. So, if I introduce a buffer, buffer again regenerates the signal, makes it again very nice. And thirdly, it can help to shield capacitive load on the output side. Like for example, I have a buffer and at the output of the buffer there is a big capacitive load. There are two capacitive loads which it was driving. Now, suppose I introduce a buffer and from that buffer I am driving one of the loads and I use another buffer, I am driving another load, that the other load. So, I am sharing the load among the two buffers and the actual gate which was driving initially, that is getting shielded. It is only driving the buffers, not the capacitive loads. Okay. So, these are some techniques. There are some improvements which can be done. But of course, there are some obvious drawbacks. Buffer means some additional electronics. So, as I said, typically they will consist of two inverters back to back, means 4 MOS transistors. They consume more area, they will consume more power. So, modern EDA tools, they use buffers quite a lot, because as you know that today's circuits are becoming very much performance aware. There is lot of performance driven optimizations which are carried out, and buffer insertion is treated as a very popular technique. So, in modern designs, typically buffers can comprise 10 to 20% of all. See, buffers are also some standard cells, right? So, means out of all standard cells, 10 to 20% can be buffers, and it can go up to 40% also in some designs. This has been observed. Okay. So, buffers, although they are very good in providing some very desirable features, but there are some drawbacks as well. You have to remember this is like a trade off. So, let us see how buffering can improve. Let us take another example of a 2 input NAND gate which is driving 5 fan out lines. So, each of them with a capacitance value of 1. So, the total load capacitance will be 5 femtofarad and you are using VB, the second gate. Now, in this graph we have shown only up to 3. So, we have not shown the whole thing, just I have noted down here. So, if you are using the intermediate VB, then for 5 picofarad 5 FF femtofarad load capacitance, the delay comes to 45 picoseconds. Okay. So, we have used this value. For this case, the delay of the gate will be 45 picosecond. But suppose we modify this fan out structure like this by inserting a buffer. First to D and E we keep as it is. This Y is a buffer, we use it to drive the remaining 3. So, you see now VB is also driving 1, 2 and 3, Y is also driving 1, 2 and 3. Let us assume that the input capacitance of Y is also 1. So, this will also be 3 femtofarad, this will also be 3 femtofarad. So, VB with 3 femtofarad, how much it is? 33. 33 is the delay. So, this gate will have 33, this will have 33 again. So, the total delay will be 33 plus 33. But this gate delay was 45. Now, this has decreased to 33. So, if this D and E are some destination where the signal has to be transmitted earlier, they have earlier required arrival times, then you can use this strategy. Okay. So, although the total delay is 66, but some of the outputs you can drive with a delay of 33. Okay. This is of course much faster than 45. Okay. So, this is what we have already said, this already we have explained. So, with this we come to the end of this lecture. In the next lecture we shall be looking at some other physical design techniques where netlist, restructuring, various techniques we shall be looking at. So, how we can adjust the delays first. You see, this kind of delay adjustments are very commonly required for timing driven adjustments and constraint satisfaction. So, whenever you have some kind of negative slack somewhere, you have to adjust the delays somehow to make the slack either 0 or positive. These are some of the very commonly used techniques. Today we have seen gate sizing and buffering. Buffering again we shall see later in a slightly different context, but for the time being, thank you.